Yeah, it sounds good.
Okay.
Hello, everyone.
Hello.
Welcome to the new room. I want to just introduce Kobi, who's going to be talking about Plumo. What we're going to do is we're going to do this talk, and while he's speaking, feel free to ask a question in the Ask a Question thing at the bottom, or potentially have a chat as well. At the end of this session, we're going to be doing the Q&A and actually get a chance to dig in a little deeper into Plumo. So please take it away, Kobi.
All right. Thank you, Anna. Very, very excited to present in the ZK Summit. So yeah, I'm going to tell you a bit about Plumo. Plumo is the light client we've been developing in Celo. It's joint work with a bunch of people. Specifically, it's Marek, Asa, Michael, Ariel, Eran, Philip, and Sai. A bunch of smart people that have been working on this. And yeah, I want to tell you about this Snark-enabled light client. Okay. So why Plumo, or what is Plumo in general? What does it mean? So let me share. Plumo actually means feather in Esperanto. So it's a kind of play on words. It means that, okay, just a second, I have a technical issue. Sorry. Okay. So it means that it's a light, very, very light client. It's lighter than a feather. And the goal is to make a light client that is very efficient to instantaneously sync to the latest state on a chain without having to download a lot of data and without having to perform a lot of computation. So let's start a bit with the motivation of why you would want such a client. So if you look at the Bitcoin chain size in general, you can see that it has been growing steadily all the time. It's a few hundred gigabytes right now if you want to sync a full node. And that's something that is not doable for normal clients to work with. So let's say that I have a mobile phone that wants to sync to the latest state of the chain. If they actually want to perform full verification of the chain, which means downloading all the transactions and processing them, that's not something they can do. Especially if it's someone that wants to just download the latest state of the chain and without waiting a lot of time. Okay, sorry, I have to pause for a second because my presentation is messing up. Let me see if you can all still see my screen.
Yeah, we still see it. It looks good.
Okay. Yeah, it was just jumping between slides automatically.
Okay. Well, I guess from where we're sitting, it looks pretty good, actually.
Okay, cool. Thanks. All right, so first motivation point, it's hard to sync a full node. On the other hand, we have a growing number of resource-constrained devices in the world. Specifically, if we look at mobile devices, we have a bunch of them already existing in the world. You actually have like 8 billion mobile devices that are active. And if you look at the numbers, it's maybe surprising, but 6 billion of them are smartphones, which means that they can run advanced software. So that's something that we can work with. Another point to make is that there is a growing interest in something called CBDCs, central bank digital currencies. And these are currencies that are run by countries, and they're going to use private blockchains. And if we want them to be actually useful in the world, we need for them to be communicated with other chains. So for example, you would want them to communicate with the Ethereum blockchain and somehow be able to transfer currency from here to there. So this is something that you would normally achieve by having a smart contract, for example, on Ethereum, verifying the private blockchain light client protocol. And when you have that, you have a smart contract that can reasonably talk about what are balances of addresses and so on. And if we're talking about resource-constrained devices, smart contracts on Ethereum are even more resource-constrained than mobile phones. Things are very, very expensive in the EVM. But yeah, people don't actually sync full nodes when they want to interact with blockchains today. And Satoshi actually came up with a very efficient way to sync with the chain without having to process all transactions, but still achieve reasonable security. And that's something called Simple Payment Verification, SPV. And the way it works is that instead of downloading all the transactions in the chain or downloading all the hundreds of gigabytes, you just download the headers of the chain and verify that the proof of work puzzles are valid and so on. And now whenever you want to make a transaction or whenever you want to query some information about the transaction, whether it was included in the past and so on, then you can ask other nodes to give you this transaction data. And with the headers that you downloaded, you can verifiably check this. But this is still not perfect, because if you look at Bitcoin, which has a very long block time, you already need to download, let's say, tens of megabytes, at least. And if you look at Ethereum, you have to download a few gigabytes. So it's still not exactly what you want if you want to instantaneously sync to the latest state of a blockchain. More specifically, if you look at the new style blockchains, such as Celo, then a lot of these use proof of stake. So in those chains, the block time is even shorter. It's a few seconds. It's less than 10 seconds, sometimes even less than 5 seconds. So if you had to download all the headers, then you would be in a bad state. You would have to download gigabytes just to sync to the latest state of the chain. Yeah. So to summarize, it's just too much data for a permissionless mobile wallet that works on a blockchain. Yeah. And it's specifically also too much data to create a trustless bridge between two chains. So one example of an attempt to do this was BTC Relay. And BTC Relay was a really cool project done by really smart people that tried to verify the Bitcoin headers inside Ethereum. And it ran for some time successfully, but the cost of maintaining it became really high, partly because of the Ethereum price, and partly because it's just expensive to verify each Bitcoin header. And if you look at the current state, it hasn't been active for almost 2 years. So there are already data points that show that this needs to be solved in a better way. We're not the first ones to talk about these problems. There are other people that have been thinking about this. So if you look at other works like NipaPow and Flyclient, they also talk about how to sync to a latest state of the chain very quickly. In Flyclient, it's even something that's logarithmic, which is about 0.5 megabyte for Ethereum. And they're very good works, but unfortunately, they work on proof of work blockchains, and they don't really work on proof of stake blockchains or any other chains that don't have a fork choice rule. So this is doesn't work for all the use cases, and especially all the new proof of stake chains. Another solution is Coda, which is also a really cool solution that actually achieves higher security than just verifying a light client protocol. In Coda, you actually verify something that is akin to verifying a full node. So you have a snark proof that shows that all the transaction has been processed correctly, and the state that you're receiving is the latest state of the chain. It's very strong. It's strictly better than SPV. But there is a trade-off. Because you have to verify all of these transactions in a snark, you limit the flexibility of what these transactions can be. So that means that you can do payments or some other simple forms of transfers, but getting fully fledged smart contracts like the EVM is going to be very hard. Additionally, in the past, Kobi used a pair of MNT curves in order to do the proof technique that they use, the recursive proof composition. And these curves are pretty expensive for our case. They're 760-bit or even 80, and that makes them very slow, both to prove things and verify things. So how is Plumo different? So first of all, Plumo works in the context of Celo's proof-of-stake protocol. And what is this Celo proof-of-stake protocol? If you look at the consensus protocol, it's a BFT-style consensus protocol. It's similar to Cosmos, for those of you that know Cosmos. And essentially, you have a set of validators. And this set of validators, at each block, have to sign the block header that they deem to be valid. So there is a proposer that sends a proposal for a block. And if all the other validators in the network agree that this block is valid and the state update is correct, then they sign this. And eventually, if we have enough signature, more than 2/3, then we can deem this block valid and propagate it to the other people in the network. And where does proof of stake comes in? Every some time, there is an election that chooses what are the next validators that are going to be validating on this chain. So how would the light client for this kind of protocol look like? It's very simple. A light client would download the headers, sends the Genesis block. So very similar to what you would do in SPV. And you could then make Merkle proofs or Merkle queries in order to know bits of data in the chain. So Celo is also EVM based. So in the headers, you have a state root. And now if you want to know the balance of an address, for example, you can give a Merkle proof that shows what is the balance of this address. Now, the difference between that and SPV in proof of work blockchains is that instead of verifying the proof of work puzzle, you verify that each block has enough signatures. And that's the way you say that the block is valid. The next thing that you do is whenever there is an election, wherever there is a new validator set chosen, you need to update your own state as a light client that you know what is the new validator set that you should be verifying the signature against. In order to help you with that, the validators, when they perform an election, include in the block header a diff, which is a diff between the current validator set and the new validator set. So that means that in order to sync to the latest state in the chain, you don't actually need to read like the smart contract that contains the election results and so on. You can just look at the headers to know the current validator set. But that is nice, that works. But like I said, if you have to download all the 5-second blocks, so a block every 5 seconds, that already becomes a lot of data. So we want it to be better. Moreover, if you use something like naive signatures, like ACDSA signatures, then imagine that you now have 100 validators. And these 100 validators sign the block. Let's say 70 of them sign, more than 2/3. And now each block would contain 70 signatures at least, or something like that. And that grows very quickly. So that's not something you want to do. So how does Plumo improve on this? The first thing it does is it introduces epoch-based syncing. And what it means is that you can't perform election in every block. You can only perform elections at epochs. So in the Celo protocol, it's around 17,000 blocks. And that means that an election occurs once a day. So if you want to sync to the latest state of the chain and to know the current validator set, you only need to download these blocks where elections are performed, because in other blocks, the validator set doesn't change, so you can skip them if you don't care about their content. The next thing we do is we use BLS signature aggregation. And this is something we'll cover later. Don't worry about it. But essentially, instead of having 100 signatures or 70 signatures in a block, BLS signatures allows you to non-interactively aggregate them into a single signature. So instead of having 70 signatures in a block, you have a single signature and a bitmap that says which are the validators that signed, that participated in this signature. So that's already a great reduction in size in both of these solutions. But this still wasn't enough for us, so that's where snarks come in. So now instead of downloading all of the epoch blocks, so a block each day, which contain a single signature, we want to do better. We want to download maybe, let's say that I joined the Celo network after 6 months. The Celo network has been running for 6 months now. So I don't want to download a lot of epoch blocks in order to sync. I want to download a single snark proof that just shows me the latest state of the chain. So that's the snark-related innovation that Plumo uses. So let's recap. What are we trying to prove? I quickly went over what is the light client protocol that we want to prove. And that's exactly what the snark does. It essentially verifies that the light client protocol performed correctly and saves you from downloading all these different epoch blocks. Essentially, you can imagine that instead of downloading all these different epoch blocks, you can just receive as an input, let's say, the validator set that existed in the Genesis block, and the validator set that has evolved after 6 months of this chain running. And you don't have to see any validator sets in the middle. So you receive this input validator set, output validator set, and a proof. So in each epoch in the proof, what are we trying to prove? So the first thing we want to show is that in each block, we aggregate the public keys from the header according to the bitmap that exists in the header. The second thing we want to verify is that each block was signed by more than 2/3 of the validators. We want to check that this is in the next epoch and not the previous one. We then want to make sure that this epoch is encoded correctly and hashed to some form of hash to group, which I'm going to cover soon, in order to verify the BLS signature on them. Now, if we perform these steps for each epoch inside a proof, and we perform many of them inside a single proof, that means that I can completely hide all the intermediate processing from clients. So how would you do such a thing? So a first approach would be to use recursion. And recursion means is that, let's imagine that you have a proof, and in each proof you do this process. And then in the next proof, you don't only do this process again for the next block, but you also verify a previous proof that the evolution of the validator set is what you expect it to be. So let's say that proof 0 talks about the evolution from validator set in the Genesis to block 1, and proof 1 talks about validator set 1 to validator set at day 2. Then when pi1 is produced, the only thing you have to show now is validator set at the Genesis, validator set at day 2, and pi1. You don't have to see pi0 anymore. So that's nice. But you can also do something that is simpler. You can run a bunch of epoch transitions inside a single large proof, And whenever you run out of space in this proof because of efficiency reasons and so on, you can create a new proof. And now whenever you want to make sure that these two proofs talks about the same chain, you need to see that the output of proof 0 and the input of proof 1 line up. So let's say that proof 0 is between time 0 and 2 months. Proof 1 is 2 months to 4 months. You just need to see that the validator said that was output at the end of 2 months is the same one that was input at the beginning of the 2 months for proof 1. So that's already nicer. But I just mentioned a lot of motivation, so let's talk about the math of BLS verification. So BLS verification uses pairings, and it uses some elliptic curve operations, and it has a few interesting properties that make it attractive for this kind of use cases. So quickly to recap how BLS signature properties makes things easier, we can see that one signature verification is this simple pairing equation. You have a signature sigma, and you have a message that is hashed to this G1 group in this elliptic curve. And you have a private key X and public key XG. And this is the way you verify BLS signature. But if you have a bunch of signatures on the same message, you can actually just add up all the different signatures and add up all the different public keys and still perform just a single pairing equation that involves only 2 pairings. So that's a nice property. Also, if you have multiple signatures on a different message and also potentially different signers, you can also do this thing better than just doing 2n pairings naively. You can also add up the signatures, but on the right-hand side, you perform a multiplication of n pairings. So it's the hash of each message, and it's also the aggregated public key for each of these different signers. Another optimization that you can make is instead of doing 2n+1 pairings, you can actually just run the product of n+1 Miller loops and just run the final exponentiation once and check that they're equal to 1. That these are standard techniques. So now we've talked about how we actually do these things in general. So we need to verify BLS signatures inside a snark. And that's not something we can usually do, because running pairings inside a snark is something that is problematic. So how you can do this? In order to do this, we use depth to recursion. So we use a pair of curves that has been introduced by the smart people of the Zexi paper. And these are a pair of curves that such that we have a good security curve, BLS 12-377, that allows us to do reasonably sized BLS signatures. And that's what we use for BLS signatures. But there is another curve, a curve that embeds BLS 12-377. And this curve allows us to create proofs about BLS 12-377. So we can actually do pairings inside the snark proof that is created on SW6. But we have another problem. If you remember, I mentioned that in order to verify a BLS signature, we actually have to hash to group. And what does that mean? It means that I have to take a message, which in our case is going to be the validator set changes, the election results essentially. And we have to create a point inside the G1 group of this elliptic curve that such that we don't know the discrete logarithm of. So some people make the mistake of trying to hash the group by just hashing the message into some random number and then multiplying it by a generator. But that's insecure. If you do that, you can actually create fake signatures. And that's not really good without knowing the private key, of course. So, but alternatively, if you do this outside of snarks, it's easy. You just use something like Blake2 and then try to interpret the random bits that you get as a valid x coordinate, and then you get the matching y coordinate. You choose one of the two according to another random bit, and eventually you get a point that you don't know the discrete logarithm of. But running Blake2 inside the snark is very expensive, and it costs about 20,000 constraints per 512 bits. And our validator set diffs are large, so running this inside the snark is going to be hard. So in order to cope with that, we use a hybrid hash function. So instead of doing directly Blake2, we first compress the message. We take the message, the large message, we run a collision-resistant hash function, and this hash function is actually the Bow-Hopwood variant of Pedersen hash that Zcash developed for sapling. And this is only collision resistant, so we can only use it to compress the message. We cannot use it as a random oracle, essentially. We cannot derive random bits out of it. So after we run this collision resistant hash function, we run Blake2. And now we can derive random bits that allows us to derive this point that we want. Of course, later on, we need to clear the cofactor and so on, but these are easier steps. This was the crucial part. Right. So let's talk about how these things look like in real life. So first of all, we should say probably thanks to Skipper Lab, which developed the amazing Zexy library that we base a lot of our work on. All of our code that implements all of this protocol is also open source. So if you want to do something like this yourself or integrate something like this, feel free. We can share the links later. And we are happy to say that we've contributed a lot of this work back to Zexy already. So if you want to do point compression or this Bow-Hopwood efficient variant of Pedersen hashes or smaller than gadgets and so on, you can already use Zexy to do them. Right. So how does this work in real life? If you look at the numbers that we have here, these are numbers that show how much time it takes to generate a proof. If you look at the proof time that runs on this SW6 curve, the one that does the heavy work, you can see that if you want to run for, let's say, 180 epochs, which corresponds to about 6 months, then it takes about 2 hours. And that sounds like a lot, like, wow, that's a lot. But that's not really bad, because this is something you have to run once. So in contrast to, for example, solutions like other solutions, you only need to run this, let's say, every few months. So you can use whatever strong machine you want. You want to do that. You don't even need zero knowledge, so you can do it on any machine. So just boot up the strongest machine that you can and compute the proof. And that's what we did. We booted up a Google Cloud machine that has 160 CPUs, 3.5 terabytes of RAM, and it takes there 2 hours to generate a proof. But that's okay. And the proof size is also okay. It's about 0.5 kilobyte and a bit of data to encode the validator sets as inputs and outputs. As to verification, which is actually what we wanted to optimize, we tested mobile phones. So we took the weakest phone that we could find on browser stack, which was the Motorola Moto G2. And even on this weaker phone, verifying this proof took about 6 seconds, which is not that bad. It's still very, very fast to sync, and it didn't have to download a lot of data. And on newer phones, it's almost instantaneous to sync. In the context of bridging or these CBDCs or just cross-chain communication, this is also realistic. So if you assume EAP 1962, which talks about generic elliptic curve computation in Ethereum, or equivalent EAPs that talk about specific curves, like the specific SW6 curve, then you can see that this is already realistic to verify these proofs in Ethereum. So it would cost about 4 million gas to verify a single proof that could spend any amount of months that you want. And then once you have the state root in the output of this proof, or more correctly, a signed state root, then you can just do Merkle proofs and see balance of addresses or fields in a smart contract and so on. So if you look at the gas prices today, it's going to cost about $6 to do this verification. So that's nice. So we're almost at the end. So let me just cap some possible improvements that we are thinking about. And before that, maybe I should mention that we're exploring how to do this trusted setup for these large curve efficiently. So people know about doing trusted setups. They know about it from Zcash, from Ethereum, from Filecoin and Aztec and so on. And here we need a trusted setup that is pretty large on a pretty large curve as well. So let's say 2 to the 26 constraints and so on. And this already takes days to do on a normal PC. So we're looking for ways to improve this, but we actually already have code working that can perform trusted setup for any ZXC curve. So some improvements that we've been thinking about are these, just replacing the SW6 curve with another curve that is just more efficient. This is a curve that has been introduced by the smart people in EY, and I think you're going to hear about it today, so I'm not going to talk about it a lot. Another approach is to use other kinds of recursion. So instead of using the ZXC style to depth to recursion, we can actually use full depth recursion. So something like half pairing halo that Coda has been pioneering. But that's a bit more novel, so we chose a more conservative approach, but eventually when these things become more widely accepted, we could do something like this. We could look at other approaches to recursion, which is plookup, which is also going to be described today by the Aztec team. And we can look about how to improve the light client protocol. So for example, to answer questions like, was transaction X included in some block in the past? We can't answer that right now. We can only answer questions about the rate state root. So if you want to answer these kind of questions, we have to introduce more data into the protocol. Yeah, and that's what I had to tell you.
Cool.
Cool. Okay, so I'm going to open up the chat now.
Yeah. So do you want to check out the Ask a Question?
Yes. Okay.
Clapping. This is what you miss a little bit from the not live version.
Yes, I even got a calp, which sounds really cool. Okay.
All right.
So let's see. Questions and answers. Would it be fair to say that Plumo does not solve the data availability problem for light clients? If so, how does cell address or mitigate the data availability problem for light clients? That's a question by Justin Drake. Yeah, and that's a very good point. It does not, Plumo directly does not solve this data availability problem. And in order to cope with that, we actually have in the Celo protocol some incentives for full nodes to provide data for light clients. So I hope that gives some intuition of why it's going to be better. But we also know that light clients usually have enough sources to ask data from. But yeah. So these combinations are good. All right. The next question by Alistair. Are the signers public? I thought you were. Okay. I thought you were using aggregation rather than threshold BLS for accountability. If not, why not use threshold? That's a great question. The signers are indeed public, and if you look at the election results, you can exactly see who are the signers. And we do use aggregation. That's why we include a bitmap in each of the blocks to tell us what are the public keys that participated. And then you have to aggregate these public keys in order to verify the signature. So threshold BLS is very nice, but then you lose two things. You lose accountability. You don't know exactly if someone provided the wrong signature or whatever, and you don't know exactly who participated to provide rewards. So that's a bit of a problem. And the other thing is that it's pretty hard to set up. In order to set up threshold BLS, you need to do a DKG. And that's something that is just significantly harder than doing aggregate BLS signatures. So we kind of emulate threshold BLS. Okay, the next question. What is an MMR? Yeah, I didn't say. An MMR is a Merkle mountain range, and you can actually think about it just as a Merkle tree. And in Flatline, they introduced this MMR as something that accumulates all the block headers that existed in the past. So if you look at the last block, you can just have this Merkle root that allows you to make efficient queries about past blocks. So in our case, if we look at the latest block, we have assigned you could, if you improve the protocol, or if you change the protocol, if you really care about it, you could look at the signed MMR root and just do queries about past transactions and past blocks. All right. I think we have a last question. Have you thought about using a Stark for the outer layer inside of a Snark? Starks can be done in prime fields of any size, so you would not need to deal with funny curves, and they would have lower prover costs. Verifier costs would increase, but Starkware has shown that fitting a Stark inside an Ethereum block is possible, and that was pre-Istanbul. That's a question by Vitalik. Yeah, and that's a very, very good question. We have been thinking about these kind of things, and we've eventually opted with Snarks for a few reasons. And I think the main reason would be that we really, really wanted to optimize for both verifier computation and the data that you have to download. And when you use a Stark, you improve on prover cost, which is actually not our problem. And you would make proof sizes much larger, especially when you want to make proofs about this large amount of epochs as we want to do. And it would also make the verifier costs increase. So we really wanted to optimize for the best verifier cost that we could get. Okay, so I think we have another question. Do we have time, Anna? I think we can't hear you.
Sorry, it was muted. I think we have, this is probably the last question that we can do here.
Sounds good.
And then we'll wrap.
Sounds good. So the question is by Luis. In the Flatline paper, they claim you could adapt Flatline for any consensus algo. Have you looked into this direction? Yes, we definitely have looked into this direction. And it's not for any consensus algo. It's for any consensus algo that has an equivalent of a longest chain rule. And to be honest, I've even asked the authors about this. And the only other reasonable consensus algorithm that might work with this would be Ouroboros, that seems to have a longest chain rule. But the authors have not worked out the full details of how it would work. So it's not sure that it could work for the use case at all.
All right. So I think that ends our session on Plumo. I want to say thank you so much. You can see a lot of claps in the chat.
Yeah.
And next up is Justin Drake talking about Plunk. I'm going to head over there now and get him set up. Okay.
Thanks for listening, everyone.
See you soon.